Hello students, in today's class we are going to see the topic of electric current. So far we have read about the static electricity, like the static charges, the charges which are not in motion. To understand what charges are and how these have different sorts of properties. Now we are working with the current electricity, and here knowing what is current is extremely important. So the very first phenomena which occurs when a charge moves gives rise to current. It is basically defined as the amount of flow of charges in a given time period. It is very much important to note over here that whenever we are defining the current, we cannot simply say it is the motion of charges, but we have to say the motion of charges in a given time period. This is related to the time. So I is given as Q upon T, where Q is the charge whose unit is coulombs and time have a unit of second. So our I current unit is coulomb per second, which is in short written as amperes. And the symbol for writing ampere is A. So this is how the current is defined. Now we will try to understand what basically the current is, how the charges are flowing, what sort of flow of charges is considered when we are trying to define the current. Let's imagine a small area held normal to the direction of flow of charges. Like our charges are flowing in this direction, we can assume, and we are considering a extremely small area ds, where S is the area. Okay, so in this both positive and negative charges can flow forward and backward across the area. So there is no such limitation that only the positive charge should flow or only the negative charge should flow. Both will flow. One will flow from the backward direction and other one will flow from the forward direction. Okay, move ahead and move back. Move ahead and move back. If in a given time interval t, now we are introducing time interval because the motion of charges alone cannot define the current. So when we are considering this time interval t, let q plus be the net amount of like positive charge that flows in the forward direction across the given area, forward to backward. Similarly, let Q minus be the net amount of negative charge flowing across the area in the forward direction in the same given interval, time interval. In the same time interval. Now the net amount of charges flowing across the area in the forward direction in time interval t is given as Q equals to Q plus minus Q minus. Like how much you are earning minus how much you are spending will give you what amount of money you are left with. Okay, amount of money left. Similarly, the total charge, net charge, equals to positive charge moving forward minus negative charge moving backward. So here it is. Then we'll get the current I equals to Q net, total displacement of the charges. Q net is the displacement of the charges divided by the time in which the time period we have defined this displacement. So mostly these currents are not steady. Hence we define this current in a different way because this is not steady. If we have said this is the area under the consideration, in this area maybe the charges coming to this area are approximately 10 but will cross only 8. So they may be diverging, they may be converging, they can be anything because they have their own interactions. They can show any sort of motion. So in such a case, we cannot define they are moving in uniform and number of charges, net number of charges will be equal to this, this and this. No, it is not possible. We have to take some limits and we have to integrate over the full area to understand what the truly current is flowing. Okay. Now what we'll see is we'll see this change in the charge del Q. Del Q shows us the change in the charge, be the net charge following across the cross section of a conductor during the time interval of del T. So we have taken from this small area, this small charge is passing in a given small time, del T. Then current at time t, current at this time t across the cross section of the conductor during the time interval is defined as the value of ratio of del q to del t in the limit of del t tending to 0, and it is given by the formula of our t as a I as a function of time, where limit for the given time tends to 0 into del q upon del t. Over here also you can see they have given us that the current is a function of time. Current is function of time. Okay, so this is in general the like formula for explaining the current. Why do we need this formula? As already has been explained, from a given area it is not defined that number of charges flowing will always be equal. If, just see over here, if we are taking like a area, this is my one of the area, and from this particular area we know that the number of charges which going to flow are 10, and similarly we have another area. From here also number of charges flowing equals to 10. What this shows? This shows that the charges are coming in a straight line and these charges are moving in uniform motion. These charges moving in uniform motion. But it is not that true, because the charges which are like plus q and minus q will show attractive properties and hence over a time will show some convergence, whereas a charge which is plus q and plus q will show the repulsive properties and may show some divergence at a time. So what exactly happens, instead of going in this way like straight like this, they tend to move like this. They will show little divergence or will show little conversion. So see, in this area flow is lesser than this area, and here the flow was more, and in this area the flow is less. So this is known as unsteady charge. Unsteady charge, the charge which is not constant or which is not steady. So this will give rise to unsteady current. Okay, so that's how we define the current as steady current, uniform current, and non-steady current, that is non-uniform current. Current, uniform and non-uniform. Now the basic concept over here is, why do we need the current to be uniform or non-uniform? We have read in the very first class in the introduction of the current electricity that uniformity needs to be maintained. Our lightning thunder lights in the climate change comes with a very non-uniform flow of the current, which results in many hazards. They may burn buildings, they damage electrical supplies over the earth, and much more. So these kind of unsteady flow of charges can be very less at some time and can be high, very high at the other time. When it is less, it have like less voltages and other properties, but naturally they do not harm. But if our current is becoming very much high, it causes a lots of hazard. And basically, naturally the lightning which is occurring causes a lot of hazard, but in our day-to-day life where electricity is needed, and in that case if we see, our electrical appliances can get damaged. So this is one of the reason why we need to like make the current uniform for our household supplies. Now we'll move on to SI unit of the current. SI unit of the current is ampere, or we can write it as coulomb per second per minute per hour. It depends in which time unit we are like seeing the flow of charges. Okay, but basically it's coulomb per second, and ampere is the standard international unit of ampere. This current is defined through the magnetic effect. This thing we are going to see in chapter number 4 and 5, the upcoming chapters. Okay, how the magnetic effect help us to define the current. Okay, current is a current is something which is related to electricity because it generates electricity. But moving charges get influenced under magnetic field also. So these properties we will see in chapter number 4 and chapter number 5. Now average lightning, the average lightning which we see in our climatic changes, climate, or in our atmosphere, carries current in the tens or thousands of range. It will range from 10 ampere to 1000 or 10,000 amperes, which is very high. Check your cable charger, check your electrical appliances. They have always written 0.1 ampere, 1 ampere, extremely less. It is not always like in the tens, also you will rarely find. Then when we go to the human nerve, where do the human nerve exist? They are in the brain of the humans, and in this we will see electrical conductance. In human nerves we can see electrical conductance carries currents in the range of microampere. Like they have the range of current which is very small, extremely small, in the range of microamperes. How much is 1 microampere? 1 microampere is equals to 1 into 10 to the power minus 6 amperes. So see the range, it's extremely small range, extremely small. So if you are holding a cable containing 0.1 or 1 ampere of charge, you will definitely get shock, as your body is a conductor, so it will get shock and you may get paralyzed. Why so? Because our brain do not have this much of capacity to hold this high current, 10 to the power 6 times higher current than the natural current which is flowing in our nerves. Okay. Now, as we have seen this thing like shock and our conductors body, as I said, human body is conductor. So in next class we are going to read about the conductors. what are conductors, how conductors help in the electrostatics, how conductors helps in the electrodynamics, how the current flowing in a conductor, what are the principles behind the flow of the charges in a conductor, is it possible to see the same in like our insulators and all. That is all what we are going to read in our next class. So in today's class it's all, and here we have learnt about the current, definition of current, formula of current, SI unit of current, and average lightning range and average human nerve range is what we have read in this section. Okay, so students, bye bye, have a good day. In the next class we will start with the properties of conductor and their relation with the current, electricity and flow of the charges. Have a good day.